Good afternoon, folks. So today I want to talk a little bit about the sort of movement AI that we're going to implement into our game for our enemies and our boss. Right now, the lecture today is mostly just going to be talking about how a movement AI sort of works, and we're going to take the simplest example of that, what's known as Kinematic AI. Just recently, I didn't put this up until not too long ago. I have yeah. So I added it to our lecture 11B. It's just a public repository. I had to check if it was public or not. It's what I'm going to go into here in just a second, and we're not necessarily going to use this for our use this exact thing for our Spectre project. But this sort of shows you how the kinematic AI can work in a real project. I wrote this little kinematic AI thing in Unity probably like 4 years ago. So it's done in a way that I would probably do it differently now. That's typically how it works for programming stuff. You sort of realize years later that you probably should have done this differently. But it is an example of how some of this kinematic AI stuff can work. So if you do want to open it up, it was done back in like Unity 5, so you'll have to update it to the sort of most recent version. There's not a lot in here. There's just a couple of cubes and a plane. And what happens is this blue cube is sort of wandering around. So it's doing this what's known as a kinematic wander. And we'll talk a little bit about that. And then the red cube is doing a kinematic seek. So the red cube is going to be following the blue blue cube around. When the blue cube goes off of the sort of game region here, the plane, the red cube won't follow it off. It'll just turn and sort of follow it to wherever it's located. So there is no sort of the red cube never goes off the bounds of the map, where the blue cube just reappears on the other side. So this is the type of movement AI that we're going to talk about today. So this is a seek. So the red is doing a seek on that blue target, and the blue is just sort of doing a wander. And you can kind of see it doing that. It's sort of changing direction, not very much. It's just it's just doing this sort of random thing. So it'll sort of go along in the same direction and just sort of randomly do it. So you can kind of think of it like a random walk, kind of, but it doesn't pick a completely random direction. It picks a random direction within a certain region of the way direction it's already moving. So it's not like randomly turning around and stuff. It's just sort of moseying along, more or less in a straight line. The red one is the one that's doing the seeking. I can also do a flee here, and we'll talk about flee as well, so running away from something. But on a map like this, on sort of a grid like this, it doesn't tend to work very well for various reasons. So this is what we're going to talk about today. We're going to talk about how you sort of get to this point. And we're not going to do any coding. The coding that we will do will be implementing this in the Spectre game. So we're not going to go in and modify this at all. But if you want to go download it, you can see sort of how the code looks. I made it somewhat generic. So there's some inheritance and stuff going on. So it might be tough to sort of figure out exactly what's going on without sort of digging into it a bit. But the basis of how this motion is happening does come from, and I've showed this book a few times, does come from this book. So this is in the syllabus. I know it's backwards in the camera, but it's the Artificial Intelligence for Games book. So the whole first section of this book is just movement AI and different types of movement AI. The first one being kinematic AI. So I'm going to talk about sort of the difference between kinematic AI and what's known as steering AI. We're not going to go super deep into it, but there are a lot of cool things in that book. So if you're interested in some of that sort of AI pieces, even if it's just some simplistic AI for a game you want to write or something, that book is the gold standard. That's the book that you should get and read through whatever appropriate section about the AI you want and see if you can get an implementation of it. So that's basically what this is. This is an implementation of kinematic AI with a couple of cubes that are in this case wandering and chasing. In our actual implementation, we're not going to create like a wandering AI and stuff. It's mostly just going to be a chase because we're always chasing after the player. So today that's sort of what I'm going to focus on, but I will sort of mention, all right, how do you run away from an enemy, or how do you do this sort of wander thing just sort of in general. But again, all of that is in the Artificial Intelligence for Games. I know that I think I mentioned this before. Professor Folagimi does offer a like an AI for games class. I think that it's like usually in the summertime, so that's something that you can look into as well. Obviously, the sort of AI. You could do multiple semesters on this stuff. So having just sort of a single lecture lets us just touch the very sort of beginnings of some of the AI stuff. So in our case, some movement AI for our different players. So I'll come back to this a little bit later on once we talk about sort of some of the code involved in this and some of the concepts. Because one of the things you might note is the red square does slow down. It's not moving at full speed all the time. When it gets close to the blue square, it will slow down and sort of turn to follow. So that if they get sort of too close, you will notice the red square not moving at full speed, whereas the blue square, the blue cube here moves at full speed all the time. So that is something that we will actually do in our Spectre game as well. We'll have this sort of slow down motion that happens. So we will talk a little bit about that today. If you do, if you do go and grab the project, you don't necessarily you're gonna have to download the whole thing. If you just want to look at a few of the scripts, you will recognize stuff that we talk about today. So even just opening this kinematic script, it has a few things, a few kinematic variables, and this update, and we're going to talk about that today, sort of how this all sort of interacts with each other. So. That's something that you can always just grab and see if you can incorporate in your game or something. But yeah, my last commit on this was 4 years ago. So that's what it tells you. It tells you how long ago it was, and that I would probably do things differently now. So I want to give just a little bit of background on some of this sort of game AI. It's not something that you're going to see in sort of a regular AI class. A lot of that these days is focused on like machine learning and stuff. We've already used a little bit of AI with our state machines, but not really in the sort of AI type context, not with our like game entities, just with our sort of game manager type stuff. So we've already done actually a little bit, but sort of nowadays in sort of a regular AI class that you would take, the focus is on things like neural networks and genetic algorithms and things like that. So this is going to be a little bit different than that kind of stuff. And one of the nice things about it is that it usually doesn't take a lot of math to do some of this more simple AI. Whereas like a neural network, you do need to be at least somewhat good at like linear algebra and things like that. We're really just doing stuff with vectors when it comes to the movement AI that we're going to be talking about. So from sort of an academic perspective, there are a few sort of AI eras. So before like 1950, so we're talking like before actual computers, that's sort of the prehistoric AI era. And a lot of stuff regarding sort of artificial intelligence was more sort of philosophical. There were some mechanical sort of novelty gadgets. There was even some, I forget the name of the game. There was a game where you would try to be, you'd use like marbles and stuff, and you would try to be like the last one to put your marble in or something. And there was an AI that was just a mechanical AI. And so it had some gears, and it would keep track of how many marbles have been thrown down, and it would always win. It was impossible to beat sort of AI, but it was all mechanically driven. So it was sort of that sort of stuff. That sort of AI was sort of philosophical / maybe some mechanical stuff that would sort of seem like it was intelligent to like always win. Then you get this era called like the Symbolic Era, and that was sort of after the prehistoric times to 1985-ish. So this was like symbolic representations of knowledge. So maybe we're just talking about certain types of variables, search algorithms, things like that. Search algorithms working on symbols, maybe on like a map or something. So this, and you may not have heard of all these things before, but things like expert systems, decision trees, state machines, which is something that we've used, pathfinding, steering, these are all symbolic sort of AI from the symbolic era that really went up, into the 80s. That was when computers started to get a lot more powerful, get a lot more prevalent throughout sort of academia and also just in sort of the wider public. So that's when this more natural AI started to appear, and that's sort of where we're at now. Like I said, if you take an AI class now, you're going to be learning about neural networks and genetic algorithms and all that sort of stuff, and these are inspired by biological processes. So, like I said, neural networks, genetic algorithm, simulated annealing. That's a simulated annealing is more of like a chemistry type process. It's like ant colony type stuff. Ant colonies do a lot of optimization, so there's sort of models based on what ant colonies do. That sort of thing. These sort of natural processes and sort of how we can mimic those to mimic the sort of the AI or maybe the intelligence that we see out in the real world. So we're not focused here. Most games don't use this sort of natural intelligence. You can, and more games are using them now than previously, trying to use some neural networks and incorporate these things into their games. But most games that you play are still using the symbolic AI. So they're still using pathfinding, which you probably heard of before. Even if it's on some forum somewhere about a game saying that, oh, the pathfinding algorithm sucks. Well, that's correct. They probably have a pathfinding algorithm that they use in the game. So largely, game AI is going to be in this sort of symbolic representation, not using things like neural networks. But that is something that is being worked on, and certain games do use things like neural networks and genetic algorithms. So if you played The Sims, which of course I think started in like the 90s, and of course have had the various incarnations since then, there were simple neural networks to deal with the behavior of the individual Sims. So there are games that incorporate some of these sort of natural AI techniques. All right, so in games, usually you're talking about like some sort of game agent, which is the game character. So like in an FPS game, an AI agent is going to be a bot. You got a bot running around, it's going to need to be doing things. So like I said, natural techniques, they're far more fashionable these days. Like I said, you're not going to get away from an AI class without learning about neural networks and stuff. But that doesn't mean it's going to be more successful. That doesn't mean if you create a neural network for your RTS game agents, so all your little agents that need to do pathfinding, it doesn't mean that if you make a neural network for them that it's going to be any better than having a standard sort of A-star style pathfinding. So not every technique, not every single technique in the sort of AI world is going to work for every game. So when it comes to actually doing some AI programming in whatever games you're making, simple is the place to start, and a lot of times simple is good enough. It sort of reminds me of I forget which Ultima it was. It was one of the Ultima Online ones. It might have been one of the first Ultima Onlines. The programmers for the wildlife in the online game. So imagine, nowadays you'd probably say like World of Warcraft or something, but imagine the wildlife in that game. Imagine it does all of the like normal stuff it would do. You get together and breed, and you eat sort of grass that's around, and you sort of do all the normal sort of natural stuff. So they had this entire sort of AI system set up to mimic the natural world for all of their sort of regular animals that were out and about. The problem was, as soon as players got in, what do? They go slaughter everything. So that was not very successful, because now there's not enough of these animals to continue with this sort of simulation of what the real world would be like with these sort of real world and AI entities. So it was great, it was complicated, and it absolutely did not work for the game. So there's a lot of situations like that. Sometimes simple, just spawning more wildlife into your games rather than trying to do a complex sort of real life AI thing was just better, because you also had that human element where, if you're in an MMO, you're going to go kill everything. So that was something that they had to deal with, and that they didn't anticipate when they originally wrote the game and the AI for all the wildlife. So not every technique is going to work for everything. That is one of the big things. So as an example, Pac-Man. So we're talking 1979. We're talking in that sort of symbolic era after when history was actually around. It just used a finite state machine. All the Ghost used a finite state machine. So I have sort of an outline of it here. It was very simple. The wander the maze was different for every single ghost. What the individual ghost did to wander the maze depended on which ghost it was, but all the rest of these sort of should make sense. If you spot Pac-Man, so if you're in some sort of line of sight, however you want to define that, then you would chase. If you lose sight, then you go back to wandering. If Pac-Man eats one of the power pellets, then you were going to run away. If you're eaten by Pac-Man, you return to base. So it's that sort of stuff. With simple state machine, only 4 states, you could probably code up something like this right now based on the state machines that we've used in the past. So you had some, enemy characters and their sort of computer controlled stuff where they use this state machine. In 94, and I remember, let's see, 94, I was in grade school at the time. I actually remember sitting in art class drawing out a map of one of the levels or something, and me and a buddy talking about it, being like, all right, well, we should send our guys over this bridge and make sure we attack the base from this way and all that kind of stuff. And that comes down to things like pathfinding. All of your units, the original Warcraft Orcs and Humans was a RTS game, so you got a bunch of pathfinding. There's formation stuff. You don't just want all of your characters or all of your all the guys that you build, you don't want all of them right on top of each other. You want them spread out in some sort of formation. So they had an AI that dealt with that. There was also some emotional models, some personality type things. This makes it sound more interesting than it was. This bullet point. It was more of the peons are going to want to flee when they're under attack. They're not going to want to sit there and fight. So that was sort of a personality type thing. In 2000, The Sims did some neural network brain, very simple neural networks, but allowed them to sort of maybe more realistically deal with sort of human behavior. And of course, at the present time, a lot of games still use very simple AI. Like I said, there's sometimes it's just easier and better to just use something simple. But there are lots of games that incorporate very complex AI. So in FPS games, you're probably going to want your enemies to do things like take cover, for instance, maybe give covering fire while other enemies move, that sort of thing. So more complex AI does make its way into a lot of these games. Real-time strategy games typically use complex AI as well. Sport and driving games use things like dynamic pathfinding. So if you're thinking, like a football game, I know that Madden hasn't been great lately, but if you think of that style of game, that style of sports game, there needs to be this dynamic pathfinding to deal with the player who has the ball or is running down the field, and what other players need to do to try to catch that human player. So there needs to be a lot more adaptability in the AI that gets used. So there's a lot of complexity that people add in. Sometimes it's good, sometimes it leads to a good result, but not always. So that's just a few examples. I mean, you can find all sorts of examples of what folks did with their AI, probably on older games more than the newest ones. The game studios tend to want to not let people know exactly how their AI works for cheating reasons and not wanting to release industry secrets. But on older games, obviously things like Pac-Man and Warcraft, there are lots of sort of articles and discussions about sort of how the AI worked then. So if you are interested in making a game that sort of does something like one of these, it can be worth going and trying to find a paper on the AI or on the AI in a particular game, or just some sort of discussion or forum discussion on, what do they do in Warcraft or Orcs and Humans to get to do their formation motion, for instance. All right, so there's really 3 main areas for sort of AI in video games. There's movement. Your entities have to be able to move around, and that's typically a single character thing. For the formation motion in something like Warcraft, you might have a bit more interaction between characters when you need to do that kind of movement. But for the most part, the single character movement that is happening in sort of this movement area. You have short-term decision making. So this is a single character behavior based on the external factors. So if the player is shooting at somebody, or player is shooting at an AI in an FPS, that AI needs to be able to make a decision to go into cover, for example. So that's sort of short-term, single character behavior type decision making. And then, of course, you need some sort of strategic AI, or there is a strategic AI sort of area as well that's more long-term group behavior. So if you play turn-based strategy games, this is used a lot in there, also in like RTS games and stuff as well. But the sort of standard sort of thinking, if you want to think of a strategic AI, you're going to think of a game like Civilization or something, where it's a long-term decisions to build a farm here instead of a mine, for instance. That's going to affect you in the long term in a game like that. Now, not all games need all of these areas, right? So a chess game is probably not going to really need the sort of movement area for AI. Movement in chess is fixed. whatever piece you are, you have fixed movement that you can do. There's no AI necessarily needs to go along with that. It's more the strategic AI that needs to be in a chess game. Whereas in a platformer, there's no need for a strategic AI. You just need some movement AI and maybe some decision-making AI potentially. So definitely not all games need all areas. The issues that sort of come up with this, and this is sort of related to all three areas, are you need some sort of input into the AI. What does the AI know? So that's sort of that information is going to come from the game world. So you need some sort of interface where the game world can output some data for the AI to take in. So when you hear about like AI cheating and stuff, a lot of times that deals with this interface. Should the AI know what the player is doing? That would certainly help for strategic decision making, for example. Should the AI know that I'm producing a bunch of melee units? If it does know, then maybe it would change its decision to produce, maybe a bunch of ranged units, so we could take out my melee units easier or something. There's also more technical things like scheduling of AI. When should you run the AI algorithms? They might be super complicated. If you have a neural network, you got to do a bunch of matrix math and stuff to be able to figure out what needs to happen. Sometimes this happens in different threads. So if you make an algorithm or a game and you make it threaded, so you're using multiple threads, you could run the AI on just a separate thread, for example. Or you could do it like on a turn-based game. You just do it between turns. You don't worry about doing any AI stuff while the player is actively doing things. And then when the turn end happens, all the AI happens at that point. So some of those technical things that you do have to think about. Things like scripting or content creation, if you add, for example, another unit or you change information about a certain character, you need to make sure that the AI can understand what change has been made. In other words, it can take that into account when you make certain types of changes or when you add new characters. This is why making AI for strategy games can be quite difficult, because if you add in some complex system, the first question anyone who's programming AI is going to ask is, how can I take data from that and have the AI respond? That's why you don't see super complex things in most strategy games, because the AI has to be able to do something with it, and it can be very difficult to take a very complex system and make the AI use it reasonably or do something reasonable about it. And then, of course, things like animation and physics. If your AI is doing something, you might need to have a certain animation for that. That sort of corresponds more to things like enemies doing their attack animation or their shooting animation or doing some sort of physics-based thing like jumping or something. You have to make sure that when the AI makes a decision or does some kind of movement, that the animation and physics is all included in that as well. So there is a lot of stuff to think about, certainly, when it comes to AI and the different types of AI that you might need. Now, of course, that AI for Games book has discussions about all of this stuff. So that's why it is so useful, because it is essentially the compendium of the sort of symbolic type AI that you could use in many, many situations. Because it is such a large book, it has a lot of little code snippets and a lot of discussion about these different areas of AI. So our focus is on movement. The Spectre game we're making is just enemies moving around the map, moving around the play area. So when it comes to movement, typically the input is some sort of geometric data about the world. So that's like things like current position of the player, current position of the enemy character, so current position of where you are, like you as in the enemy. Maybe other physical properties. There might be some pathfinding associated with it. There might be some barriers or something, like you can't go too close to the edge of the world or something. It's those sorts of things. Geometric data, so like transforms and XY positions. That's what I mean by geometric data. The output is then going to be some data representing the movement. And typically this is just a vector. That's why vectors are so powerful, and why you sort of have to understand the vector 2 and vector 3 in Unity and sort of how to work with them. This geometric data is things like velocity or acceleration. For most games, and again that we're going to write, characters typically only have sort of two states. there are at least two movement states. They're either stationary or they're moving. And moving can, of course, incorporate things like jumping and other stuff like that. But typically for movement states, you're either moving or not moving. That's just sort of a typical thing when it comes to characters in like a platformer type game, or like a game like a top-down sort of game that we're making. So these are the things that we're going to keep in mind. The input is information about the world, usually vectors and like X and Y and stuff like that. And the output is a velocity vector or an acceleration vector. So it's not, the inputs and outputs aren't too complicated, which is definitely a good thing. Today we're going to do kinematic AI. We're not going to worry about steering AI or steering behavior in this class. It is in, of course, the book, and I imagine that Professor Folajimi does talk about these when she does her AI for Games class. Kinematic movement means constant velocity. There is no acceleration. There is no slowing down. Depending on how much physics you've taken, no acceleration means positive or negative acceleration, so it means the same thing, but yeah. So constant velocity, no acceleration. It might look like in this example, in the example here of these guys chasing each other, it might look like there is some slowing down. That's kind of correct, but there is no acceleration. That's what I want to point out here in this one. Even though the red cube gets close to the blue one and it looks like it slows down, it does. It is moving slower, but there's not actually acceleration happening. And we'll talk about how you can get to that point today. Why it sort of looks like it's slowing down, but it's still just constant velocity. Steering behavior is dynamic with acceleration. So I want you to think of kinematic like this. You're moving along, say you're moving up. If you want to move down at any point, you can just move down. You can just change direction and move down. Whereas if we were doing a steering behavior, we would have to slow down to a stop and then speed up going a different direction. That's what I mean by steering behavior. So the steering behavior is more like driving a car. You can't just instantly change direction. Whereas a kinematic movement, you can. You can instantly change direction and instantly be going the sort of fastest velocity that you want to go. So steering behavior is going to be more realistic. It takes into account how fast you're currently going, and it gives you an acceleration so that you can slow down and change or just rotate, for example, just change your direction. It gives you an acceleration that will do that for you. So it tends to be more realistic, but as I'm sure you've sort of realized, more realistic typically means more potential issues. So again, that AI for Games book actually goes into a lot of the issues with steering behavior. Even though it's better, typically it's going to be better for sort of the realism of your game. There's a lot more to think about when it comes to dealing with acceleration rather than just a constant velocity. So our focus today is this kinematic movement. So this constant velocity, no acceleration. Examples of what this outputs: the kinematic algorithm outputs a direction. That's it. So essentially just a vector, in principle, a normalized vector. The steering algorithm returns an acceleration. So difference between a direction and an acceleration. All right, so the kinematic representation, the variables that we need to know about when we're doing this type of motion are position, orientation. So think of those as the static properties: where you are and where you're pointed. And it needs to know velocity, this is an important one, and rotation. So these are the vectors or the values that are representing motion. So of course, velocity, we're just talking linear velocity here. So this is just linear velocity v. It has an x component and a y component. So it's, of course, a vector. Rotation deals with angular velocity. So you can kind of think of it as like radians per second. How fast are you rotating, rather than just linear velocity, which is our motion. We're not going to deal with the angular part in our Spectre game, but I am going to sort of have it in here in the presentation because it is worth thinking about if the pointing of the object matters. So in like say a top-down like driving game or something. So I don't know, like the original like Grand Theft Auto 1 and 2, for example. sort of a top-down driving type game, it matters where you're pointed. And so you should have some sort of rotation when you're trying to turn. So that would be represented by this sort of angular velocity or this rotation. So position, orientation, velocity, rotation. Those are the 4 things you need to know in a kinematic movement algorithm. For the most part, the code that I'm going to show is from the Artificial Intelligence for Games book. The authors write this in a way that is mostly language agnostic. They're assuming like object-oriented style language, but it's mostly language agnostic. If you've never seen struct before, it's mainly representing the way that they write about it. It's basically representing a class, or it should represent some sort of class type object. If you're using like a regular C, a struct can only hold variables. So that's sort of something to consider if you're actually using a language that contains structs as a type of object. But for the most part, if you see struct in the Artificial Intelligence for Games book or in the lecture today, it's basically a class. You could basically make a class out of this. So this one's called kinematic, and it has those 4 things. So position is going to be a 2D vector. Orientation is just going to be a floating point value. Think of it like the angle. Velocity is a vector. And rotation is just how fast you rotate, that sort of radians per second or degrees per second, whatever unit you want it to be in. So in the actual project itself, the one that I have up here, I have a class called kinematic. So it is exactly that class. It contains, I use vector 3s here just for 3D space, but I have a vector 3 called position, a float for orientation, a vector 3 velocity, a float for rotation. We'll talk about this update later. And then I just have a couple of getters. I have some getters and setters for all these values, so I can get them and do whatever I need to do with them. So really, this class is almost exactly what is on that slide. This is something we'll add and will be on a slide coming up in just a moment. So that's my sort of kinematic class. That's the data that it needs to have. All right, so depending on how you want your game to look, you can have independent facing. Most of the time, your character is going to face the direction that it's moving. And in the project that I have, the Unity one that I showed, that should be the case all the time, I think. But steering algorithms, they sometimes ignore rotation. Sometimes it doesn't matter. So for our Spectre game, rotation's not going to matter at all. So we're just going to completely forget about it. But if you do want to avoid abrupt changes, so something where like you're facing one way and then the next frame you're facing a totally different way, if you want to avoid that sort of thing, you can actually do that. And this is a figure from the Artificial Intelligence for Games book, where you can start moving in the direction you want to move, but only be partially facing that direction. So there are ways to do this. So you don't always have to sort of jump to whatever facing you are. And that's where using things like a rotation, radians per second, and having that change the orientation can sort of get you to that. And in the book, they do talk about that. We've had a couple of physics lessons, or at least one physics lesson so far in the class. So I just want to sort of reiterate a little bit of that. So velocity and acceleration, they're just the first and second derivative of the position. So if our position is r, then r prime, so the first derivative of a position at some time, is just the velocity at that time. And the second derivative of the position is the acceleration at that time. Now, again, we're not worried about acceleration for our kinematic algorithm, but you basically end up with these 4 equations for position, velocity, angle, and angular acceleration. Basically angular velocity and the actual angle itself. You've seen this sort of thing before. We've done this. Specifically, we've done this one. The position equals the position previously, so the position at some previous time, plus the velocity times time. We've done that. Our time is delta time. Our velocity might be like max speed or something. And our previous position was just where our transform was. And the new position is just where we're going to be on the next frame. So we've done this piece before. If we had acceleration, we would need this extra piece here, another vector, 1/2 times that acceleration vector times the delta time dot delta time squared. Updating the velocity based on acceleration is just this. Same thing for our angle and our angular velocity. So all of these are just relatively simple equations. If you've taken the sort of engineering physics 1, you've seen these, you've derived these, you probably did this stuff with calculus and all that to get to these equations. But these are what we want to use. Now I want you to think about the kinematic movement, the kinematic steering. We have no acceleration, no regular acceleration, and no angular acceleration. So that leaves us with these 4 equations. The velocity won't change. The angular velocity won't change. So our angle and our position simply change by whatever the previous was plus whatever our rotation and our velocity are, times time dot delta time. So by adding no acceleration, it simplifies our equation. So hopefully that sort of makes sense, especially if you're taking a physics class. And this is actually why I recommend to take a physics class as an undergrad, because you sort of it helps understand where all this stuff comes from, and then it's sort of a little bit easier to grasp when you might need to use it when you're working on a game or something. So that's what we're going to end up writing. So here is that same kinematic class and this update function. Now, the update function, in this case, takes a steering. We'll talk about what that is a little bit later. And it takes a time. This is our dt. Or in Unity, this would be time dot delta time. Or potentially time dot fixed delta time if this is in fixed update. So here is those 4 equations. Our position is just our velocity times time, plus 1/2 steering dot linear. I'll tell you what that is in a second. Which you can probably guess from the equation. It's the acceleration times time squared. Same thing for orientation. Rotation times time plus 1/2 angular acceleration times time squared. And then the velocity and the rotation change by the acceleration and the angular acceleration times their time. So I'm just using the same stuff from the same sort of equations from the Artificial Intelligence for Games book, but I will show you in the code from the Unity example. Now I mentioned, so this is the full equation here. I mentioned that we don't have acceleration, so that's going to simplify a lot of this stuff. The steering dot linear, like I said, represents acceleration. So for our kinematic AI, we're either not moving at all or we're moving at max speed. So we can drop anything that has steering dot linear or steering dot angular. We can completely get rid of it. So that's it. So for kinematic steering, it's just these 2 equations. And we've seen these types of equations before, particularly with position. So in our Unity project, or in the Unity project that I put up, it's just this. So it's literally just that. I do take dt. Here I could put time dot delta time, but it's something where if I want a different dt to run the calculation with, I have that as a variable. And then here I have this steering thing. It's a different class. It's a kinematic steering output, which if we take a look at that, all that contains is a velocity and a rotation. So it's basically just a data. So you send in a kinematic steering output, and it fills in the velocity and the rotation based on this equation here. The reason why I do this is because this is the structure that is in the book. There's sort of no other reason for that. I wanted to follow along what the AI for Games book was actually doing. So that is why it's sort of set up this way. So that's it. Just update your position based on your velocity, update your orientation based on your rotation. And we don't need anything else for this one because we're only doing the kinematic steering. If we were doing the sort of regular steering with acceleration, then we would need the other equations. So it would become a bit more complicated. We have a bit more things to keep track of, that sort of stuff. All right, so very, very simple update function, which gives some good results. All right, so here's that kinematic steering output that I showed you, just a class with a velocity and a rotation. And then in Unity, I had a couple of setters and getters for those. All right, so let's talk about Seek. Seek is chasing somebody. An object is going to chase something. So the input is going to be data about you, the character that's doing the seek, and whatever your target happens to be. So if this is an enemy, if we're talking about an enemy, we need to know information about the enemy itself, so where I am, and the target, the player. The output is just then the velocity along the target's direction. Where do I need to move such that I'm going to get closer to the target? So that's that steering output. Rotation can be used as well. If I want to change my orientation, then I need to do some kind of rotation too. But the big one here is the velocity. How am I going to move such that I'm moving towards the target? So that's the input that goes into that update function. All right, I'm going to show you the kinematic seek. It's a little bit more complicated in my scripts because I have a little bit of inheritance and stuff going on, but I want to point out a few things here. We need data about the character, so in this case, the enemy, and the target. So if we say this is enemy, and this is the player. So I need to know information about that. Then I get the steering. So I get how I'm going to be moving. So I create a new kinematic steering output. Remember, this contains a velocity and a rotation. And I'm going to fill that in and then return that steering. All right, so initially I'm going to set the velocity in my steering to target position minus character position. This gives me the direction. If I am here and the target is here, this will give me this arrow. Then I normalize it. So we get just a arrow of length 1, still pointed in the same way. And then I multiply that by max speed. So we've done something a little bit like this before, where we've used this sort of normalized and we sort of multiply by max speed. This is so we move at the correct rate. Because we might be really far away. Our character and the target might be really far away from each other, in which case I'm going to get a huge vector. I want to make sure that vector does not exceed a length that equals my max speed. So that's basically what we're doing with the normalized and the max speed. And then we could do stuff with the orientation as well. We could change where this character is pointing. I'll show you this. It's not sort of too important specifically because we're not going to actually need it in our game. But you can write a function that gets the new orientation based on your current orientation and maybe the direction that you're going. So in this case, this one doesn't really use it because it sets the rotation to 0 and just says gets new orientation, and it just sets the orientation to the direction that our velocity is pointing. So in this case, we always point the direction that we're moving. And so I can show you that. I can show you that in the script. It's just a little bit of math to it. It's actually just a 2-argument arctangent, so similar to what we used with the pointing for our wand in the Spectre game. So that's the kinematic seek. This is the whole point of kinematic seek. We get this steering, which is, again, is our velocity and our orientation. Where do we send the steering? We send it into this kinematic. We send it right in here. So we get the steering. That's where we want to point. That's the velocity we want to move. And when we send it into here, we actually update the position and update the orientation. That's what we do. So that's how this works. And let me pull up the steering version of this. So everything here is in this sort of AI core thing. And we'll get the seek here. So here is the seek. So there's, like I said, there's some inheritance that happens here, but here's the kinematic seek in this project. So I have the thing here, get target vector. So that's getting that particular vector. and then it does this. It basically does this. Steering velocity, steering.velocity.normalize times max speed. So this is that thing. This gives you a little bit of jitteriness, and I have to talk about that a little bit in the slides. There is a different way to do it, and we're going to talk about that a little bit as well, but this is the way. This is essentially what it is doing. We're returning steering.velocity.normalized times max speed, which is exactly what we had here in the slides. After we got the velocity, we grabbed these, did these calculations, and then returned it. All right, so I have a little description of sort of each one of these, especially if you end up going back through this. So this one here, make sure you're moving in the direction of your target. This guy here, make sure you're facing the direction that you're moving. I'll show you the get new orientation a little bit later. And then the velocity is a speed and a direction, so we need to make sure to normalize and multiply by the max speed, so we have the speed correct and the direction correct. So that's those pieces. The nice thing about this is that it's identical for fleeing from a target, except for one change. So back in my code here, I do have a kinematic flee as well. There's not much here. I'm utilizing some of the inheritance stuff, of course, but our get velocity here is doing that exact same line we had up above. It's doing this line that was commented out. And it's doing the get target vector. But notice the difference. Target minus character position gives me the vector from my enemy to the player, for instance. If I switch that around, if I do character minus target, I get the vector pointing away from the character, away from essentially away from the player, the opposite direction. That's how you flee. That's the only difference in the fleeing algorithm. The vector is just pointed in the opposite direction as towards whatever your target is. It's pointed sort of negative to the target. That's how you flee. That's the direction you want to move. You want to move the fastest way away from the target is the exact opposite direction. So for fleeing, for running away, the nice thing is it's identical. You just change around the way you're doing the subtraction here for the direction. So that's why it was sort of so easy to write that in the kinematic flee that I had in the algorithm there. All right, so when you arrive, let's say you had a static object and you had some static thing hanging around and you had an enemy moving towards that static thing and you wanted it to stop. There's a wiggle that happens because you never actually get to exactly the position that you're trying to get to. There's always a little bit of overshot. And the reason for that is because the game world isn't continuous in terms of time. You have time.delta time. It's small, but it's not continuous, which means you might overshoot the target by a little bit. And then what does that mean you do? That means you turn around and you try to move back to the target, but you're going to overshoot again. And so you keep doing this little jittery thing, and it looks like you have this sort of jitter thing going on. It doesn't look very good. It's obviously not what you're going to want in your game. So typically what we do is we use a satisfaction radius. We say that if you get close enough, and close enough depends on your game, then you just stop. You don't worry about continuing to try to get exactly on the spot that you're trying to get to. When it gets close enough, then you're good to go. What that means in terms of speed is that you can actually slow down as you get close to the satisfaction radius. It sounds like acceleration, but it's not. It's just as we get closer, we make sure that we use a different velocity the closer we get. We use a smaller velocity than our max as we get close to that satisfaction radius. And then when we reach the satisfaction radius, we stop. So I don't have a slide that specifically shows this, and we are going to use this in our game. So you will see it again, but that's what the rest of this stuff here is in this particular one. So if the steering, if the velocity, if the steering dot velocity dot magnitude is less than this radius, that's that satisfaction radius, then we just return a vector of 0. We stop. Get velocity 0. If it's not, if we're outside of the radius, then our velocity, we're going to divide that by a variable, this time to target. And we're going to set the time to target, and we're going to see how this works in our Spectre game. Think of it as, I want to reach my target within like 1 second. Well, that's not going to happen if you're far away, so the velocity is going to be maximum. But as you get closer and closer, you're going to keep dividing, and typically time to target is not just going to be 1 to do this sort of successive division that you end up doing, but your steering velocity is going to be reduced based on this time to target, because we check if after we do this division by the time to target, we check, is that greater than the max speed, we return the max speed. So we're always going to be going max speed unless we're too close. We start getting too close, then we're going to start doing this division. So we're going to see more how this works. If you don't sort of fully understand this yet, we are going to program this up for our Spectre game. So that is something that we are going to do. Typically, you're going to call this something like arrive movement, because when you arrive somewhere, whether it's actually physically driving your car and then parking in a parking spot, you're going to do the same thing. You're going to go really fast when you're on the highway, but then as you go onto surface roads, you end up going slower and slower. And then when you finally get to the parking spot, you sort of ease right in. That's what this is meant to do. So again, if you don't fully understand this yet, and I don't have a dedicated slide to it, it's something that we will do in our game. So you will see it again for sure. Yeah, so we're going to use this sort of arrival AI on our characters in Spectre. Another useful one is wander, kinematic wander. That's what the blue cube in the demonstration today was doing. It just moves the character in the current orientation, wherever it's pointed, with a maximum speed. So wherever this object is pointed, this character is pointed, that's the direction it moves. So it's relatively simple. It's just you're multiplying by the speed times the orientation as a vector. This as vector is not a unity thing. This is from the artificial intelligence book. Just write the orientation as a vector. So in other words, the vector of where you're pointing, typically, which is normalized as well, and then you multiply that by max speed, and then you potentially change some of the rotation just a little bit. So every frame, you're going to change your rotation by a little bit. And so it has some random number stuff in here, but just think about doing a random number between -1 and 1, and then multiplying that by your max rotation. That's essentially what this is doing. And then you return that steering. So whichever way you're pointed, that's the way you're going to move. And then you potentially might move a little bit of rotation so that the next frame you move in that direction. And you don't want to make the max rotation too high or it's going to look weird. But with a small max rotation, you get some of this sort of decent motion here, where and sort of now that we've talked about it a bit, hopefully it sort of makes sense how this is sort of working here, how this wander's working, and how this guy is sort of doing his thing. I can show you the get rotation here. I think that was in the base class here. Yeah, here's that get new orientation. It's just if the velocity is greater than 0, so in other words, if you're not stopped, it's just computing the arctangent of the x and the z velocity. Remember, y in our game world, y is up, so x and z will move me along that plane that we're looking at. So it's just doing the tangent to get the angle. So it's just always pointing at the same angle that we are moving at. So that's how this red one's working to move its rotation. And that's why it flips when the blue one goes off the screen. The red one just immediately flips to point the other direction. So the movement here might look a little bit complex in that, wow, we got this guy sort of chasing him down and doing all this sort of slowdown, but really it's the code that we just saw. It's the code that we just looked at in the slides and that get new orientation that I just showed you. It's not a lot of code to get what looks like an AI agent that is trying to chase this blue cube down. So Kinematic AI, even though it is the simplest sort of movement AI that you can have, it still doesn't do a bad job. It's not terrible for doing sort of movement AI stuff. If you want something more realistic, obviously you're going to need something more complicated. But really, this might be all you need for a lot of different styles of games, and that's why we're going to use it in our Spectre game. So I know we didn't have a lot of we basically didn't have any sort of programming stuff. I encourage you to go potentially play around with this. The main here has a few things here to let us set the AI. So this is just like box 1 and box 2. So in principle, we could set both of these guys to wander. I didn't put any like menu stuff in here, key bindings. I should have put some keys in here or something long ago to do this. But in principle, you can change the AIs on them and sort of see what they end up doing. So we got a red box and a blue box that are just wandering around doing their own thing. The flea is in there as well, so you could change one of these. I think it's just flea like this. Flee and seek. This is not going to work very well, and I'll explain why once it starts to run. You will see it working at the beginning. And then it does this. And they get caught in a corner. Because this guy, he gets teleported to the other corner. And then this one wants to move towards him. So that's why this guy looks like he's on jittery. But this guy sees the blue one over here and knows I got to go the other direction. So it goes back to this corner. And then this guy tries to go that way. So that's why you get the back and forth jittery. And then this guy sees it and wants to go back. So doing it with this sort of teleporting to the other sides does not work for the flea stuff. But it doesn't mean it's not working. It actually is working exactly correctly, exactly what it's supposed to do. It's just our world is causing a problem with that. So there is some stuff that you can mess around with in here. If we did like a flea and a wander, it would work a little bit differently. But so these are. Feel free to mess around with this. Feel free to download it and mess around with it. There's a few other things in here for if you want to mess around with this sort of jittery one here, you could uncomment the return, steering velocity, normalize, max speed, and just sort of see the sort of jittery stuff that happens, for example. There are things to mess around with in here, but because I use some inheritance and all of that, it's not ideal. I would probably in the future have this kinematic AI core. I'd probably have it be a mono behavior as well. And then be able to attach it and do that sort of thing. So that's what we're going to do in our Spectre game. We're going to have it be more modular than what this is, but use the same code in a little bit simpler way, not as generic a way, but it'll be sort of simpler to understand, I hope, in our Spectre game. So that's it for today. Next time, so that'll be Tuesday. We'll be hooking some movement AI into our enemies. So we're actually going to take this, code up some of this AI. We're gonna call it. I think it's just going to be an AI movement script, maybe like a kinematic AI movement script or something, and that will implement our AI move interface. So then we can add that particular script to our game object, and then it'll all be hooked up into our enemies. So that is what we're going to do next time before Thanksgiving. So I know that it was a lot of sort of talking at you guys, but I hope that at least gave a little bit of background into this movement AI. And again, if you want to mess around with that project, feel free to do so. I gave a little short talk on it at a hackathon 4 years ago. So feel free to mess around with it and sort of see what happens when you change things and stuff. But that is it for today. So I will see you guys, I guess, next Tuesday. Have a good weekend.
Thanks, Professor. Have a good one.
See ya.